Okay, number 9. Population growth can be modeled by this exponential function. And P is the world population. T is the time in years since 1975. So part A, they want you to estimate the world population in 2015. So 2015 minus 1975, that would be 40 years. So that's 40 years since 1975. So now you can plug in t equal to 40 into your model to get the answer. So P of 40 is 4 times. So basically plug in this one. So 4 times 1.019 to the power of 40. Your calculator will tell you the answer is approximately 8.5. So that means the world population is about 8.5 billions in the year 2015, That's part A. Part B, when will the population reach 10 billion? So that means P of t here is 10. So what is t? So that's what this one is asking. You can again plug into your model. So 10 equal to 4 times 1.019 to the power of t. You want to solve for t. So you divide by 4 on both sides. This one become 10 over 4 equals 1.019 to the power of t. Then how to solve t? You take log base of 1.019 on both sides. So on the left, that will become log base 1.019. What's inside is 10 over 4, which is 2.5, equals your t. But for the calculator, they don't have the log of any base calculated. They only have base 10 and base e. So you have to use one more step of change of the base formula. So here I use the log base 10. If you want to change to log base 10, the upper here will become log base 10 of 2.5. So you copy this number here. Down here will be the log base 10 of the previous base. So that's 1.019. Then your calculator will tell you the number is 48.6825 and so on. And they want you to round to the nearest year. So is it 48 or 49? So you know at the year 48, the population is slightly smaller than 10 billion. It's not reached 10 billion yet. So we have to use 49 here. So for the population to reach 10 billion, we need 49 years since 1975. So that is the year 49 plus 1975, which is 2024. So that's for part B. Part C, what was the world population in 1975? So because T is a year since 1975, so T is 0 here. So P of 0 is, you plug in T equal to 0. 4 times 1.019 to the power of 0, which is just 4. So you know the world population in 1975 was 4 billions. That's part C. Part D, what is the percentage of the world population growing each year? So this is to calculate the growth rate. So for the growth rate, what you find is the base of your exponential function here. Use that to minus 1 and times 100%. So 1.019 minus 1 times 100%. That is 0.019 times 100%. In order to change this number into percentage, what you do is move the decimal point to the right twice. So 1, 2, which is 1.9. so 1.9%. So now you know the world population is growing 1.9% each year. That's part D. Number 10, very similar question. You have $20,000 and then the money can be modeled by this exponential function here. For part A, they want to ask you in how many years will the money in your account double? So initially you have 20,000. Double that means it's 4,000. So that means if f of t is 4,000, what is the t? So you plug in 4,000 into your function. So 4,000 equal to 2,000 times 1.052 to the power of t. And you want to solve for t. Divide by 2,000 on both sides, and then take log of base 1.052. So t is the log base 1.052 of the 2. Again, we don't really like this base here. We want to change the base to 10. So t will be log base 10 of 2 over log base 10 of 1.052. And from here, you can plug into your calculator to get the answer. This t will be 13.67 and so on. Then how to round that to the integer? Because you want the money in your account to double. You know, if t equal to 13, the money is not quite doubled. It's slightly smaller than 4,000. And in the year 14, your money will be more than 4,000. So we will choose year 14. So in 14 years, the money will double. That's part A. Part B, according to the model, how much money will the account have in 10 years? So t equal to 10. What is the f? So f of 10 will be 2,000 times 1.052 to the power of 10. You can plug into your calculator and they will tell you the money is approximately $3,320.38. So that's for part B. Part C, what is the earning interest rate? It is very similar to the growth rate. So what you need to do is first find the base in your exponential function. Use that to minus 1 and then times 100%. So 1.052 minus 1 times 100%. So that's 0.52 times 100%. Again, in order to change this one into the percentage, you have to move the decimal point to the right twice. So 1, 2. That will give you 5.2%. So the earning interest is 5.2%. That's part C. Okay, number 11. The speed and the body mass of a butterfly can be modeled by this radical function. So first, we want to use this model to estimate the average forward speed of a butterfly with a body mass of 0.5 gram. So here m equals 0.5. What is v? You want to plug into your model. So v of 0.5 equals to 8.7 times square root of 0.5. You can plug into your calculator. It will tell you the answer is 6.1518 and so on. If round to one decimal place, that would be 6.2. Because this digit to the right is 5, so you need to round up. So the conclusion is average forward speed of butterfly with a body mass of 0.5 gram would be approximately 6.2 meters per second. Again, don't forget to add your units here. That's part A. For part B, so what is the body mass of a butterfly that has an average forward speed of 5 meters per second? So V equal to 5. What is your M? Again, plug into your model. 5 equals to 8.7 times square root of M. You divide by 8.7 on both sides, and then square on both sides to get M. So M would be 5 over 8.7 altogether squared. And your calculator will tell you that answer should be 0.330 and so on. So if you round to one decimal place, that would be just a 0.3. So the body mass of the butterfly that have the average forward speed of 5 meters per second would be about 0.3 gram. So that's the conclusion for part B. Okay, number 12. You have the model L of M as this radical function. So for part A, they want you to use this model to estimate the body length with a body mass of 4.6 kilograms. So big M is 4.6. You want to know what is L. So you plug into your model. L of 4.6 is 0.330 times the cube root of 4.6. So the calculator tells you it's 0.5488. So if round to one decimal place, that would be 0.5. So you know that the body length of a mammal with a body mass of 4.6 kilograms would be about 0.5 meter. That's part A. For part B, so estimate the body mass of a mammal with body length of 1 meter. So L is 1. What is M? You can plug in the model. 1 equal to 0.330 times the cube root of M. You want to solve for big M. So you divide by 0.330 on both sides, and then raise to the power of 3 on both sides. So M will be 1 over 0.330 altogether raised to the power of 3. So M should 27.826 and so on. So if you round to one decimal place, that would be 27.8. So your conclusion would be the body mass of a mammal with a body length of 1 meter would be about 27.8 kilograms. That's part B.